Limit definition. What would the limit definition say? I've got to do plug in x plus h in minus the thing at x divided by h. Now that looks like, I do not blame you for looking at that and going, how could I do any shit with that, Jeff? But what we can do, let me see if you guys agree with me. What we can do is so cool. Remember when we had to do the product rule proof, and we had to add and subtract the same thing? And that was something you would never have thought of. But now it should be kind of like in your brain somewhere. Oh, that might be useful in certain theorems and stuff to do that. That's something I'm allowed to do that I never thought of. Well, what else could I do instead of add something and subtract something? I could multiply something and divide the same thing. Right? Now watch. So here we go. Again, this is nothing I would expect you to do on your own, because what the shit? That's nothing that's just going to naturally, oh yeah. But once I write this, let me see if you guys notice some things. So what I'm going to divide and multiply by, I got an extra or one less thing, there you go, is g of x plus h minus g of x. You guys see that? So I move the h over, I divided by this, and I multiply by this. So these are the same. The only place they are not the same is if this is 0, and these are only really 0 if I let h go to 0 and it never gets to 0. Right? There's a little bit of a, what if g itself is 0? Oh shit, let's not worry about that. Does everybody see what happened from here? Everybody see that?
I don't see it.
So, for example, if I multiply by 2, what must I do at the same time so I didn't change anything? And you know this. How do I... all right, just go with me for a second. How do I add these together? Yeah, so if I multiply top by 2, I better multiply bottom by 2, because overall, what did I just do? Nothing. I multiply by 1. So if I multiply by 2 here, I better divide by 2 here. Right? So overall, what did I just do? Nothing. Because 2 over 2 is 1. Does it look different than it did before? Yes. Is it different? No, the same way that 2/4 is not different from 1/2. Is that cool to say? We have to be at the point where we're over the factors of 2 and a 4. I don't care. 2/4 is the same number as 1/2. We know this. So I can multiply by any damn thing as long as I divide by that damn thing at the same time. And it's not 0, right? So what did I multiply by? I multiply by this. So I better divide by this at the same time. So that overall, I just didn't do anything. And I just kind of move the h over. Why? Because what's this? The limit of this is the definition of, you can do it. You got to know this form by now. Yes, g prime. Now, watch. Now this is where things get... I was going to say uber cool, but that just sounds stupid. Lift cool. Notice, now watch. Oh, yeah, I really desperately want you guys, this kicks so much ass. There's a lot of kind of different ways to do this, but I like this way, because it kind of brings us back to what is g of x really? It took the place of y, right? So what is g of x plus h? So if I have some function g, now I'll tell you this, I am assuming that these functions are continuous at any point we're trying to take the derivative of them. Is that decent? Because otherwise it's not differentiable necessarily, and then oh shit, right? So if I have g of x, whatever g of something is it that different from what it is of, so for example, here's x plus h. The output here, I can call it y. The output here should be really close to y. Is that decent? Because what's h? H is infinitesimally small. So am I really going to have my outputs move that far away? No. So I'm going to call this guy. This gets a little bit in the weeds, but I don't want to gloss over everything.
Can we draw that a little bit bigger?
Maybe. That was really just for me. So let me overstate the difference here. We all know it's a lot closer, right? So here's the output for this guy. I'll call it y. Here's the output for this guy. I'm going to call it y plus h1. Because how far apart should these two be? As I get closer and closer, how far apart are these two? Not very far. In fact, as this approaches this, this should approach that. Are you guys with me? This is really awesome. Not really squeeze theorem, but sort of, because I'm actually not having two functions that do this. I'm just making the space they can live in nothing. Yeah. So I'm going to call this. Just this is too nice to believe. Kind of just go. All right. So what's that become then? So I'm really not changing this. I'm just kind of rewording it so it's more obvious what it is. Help me out now. As h go to 0, what is h1 doing? What did we just talk about? As h goes to 0, what is h1 doing? Going to 0. So doing that instead is the same thing. So what's in here now? What is g of x plus h? Y plus h1. What's g of x? Y. What's g of x plus h? Y plus h1. What's g of y? G of x? It's y. So don't the y's cancel? Now again, let me just slow down for a minute. It is important that you see where this rule comes from, that you see that there is an overarching proof, not just, it looks like it's, no. I need to know for sure, no matter what the shit that function is, if it's continuous, where I'm interested in, there should be a proof that this guess works, that it is outside times inside derivative, right? It's got to be a proof. So there's my g prime. That's the derivative of the inside. That's like cosine. The inside function is g. So we captured that piece. This is the piece that looks weird as shit right there, but now it should look a lot better. Can I just do that just for sake of room? The y's kill each other. So what is that? We can do it. What was this? G prime x. So what's this? F prime y. What was y? G of x. So what does this say? This says whatever the outside function is, do its derivative first with that function still inside. So it's as if the inside was just x. Do the derivative of the outside function, rewrite the inside function in there. Then the inside function gets its turn on the outside. Now, I know a lot of you guys, I need you to be invested in this, but not so much that you're not able to apply the rule, right? So this is the derivation of where this rule comes from. I'm going to leave that up there, but let's do a concrete example, please, dear God, of what this thing looks like in action. Not this guessy shit. Let's just use the result we got. So let's say I have a function. What you got, Jeff? Let's see. What about 4x minus 2 to the 11th power? Before we knew this rule, what would I have to do here? I'd have to actually write it 11 times. Oh, shit. That sucks on two levels. One, I'll take a little bit of time. And two, what do I normally want to do with polynomial derivatives? Factor them. Can you imagine you're going to have all these terms and then you're supposed to factor that? Can you factor something with a 10th power in it very easily? No. So I'd rather have a rule that lets me keep it in factored form. So what's the inside function here? Yeah, the inside function is 4x minus 2. You can normally find that pretty easily. There are a couple places where it's a little bit wonky, but normally the inside function is just really obvious. It's inside something else. It's inside a square root. It's inside 11th power. It's inside of a sine, something. What's the outside power? Outside power. Outside function. What's the outside function? What is 4x minus 2 in?
X to the 11th.
Something to the 11th power, 11. So what chain rule says, nuts and bolts, not real like rigorous definition. What's the nuts and bolts idea? Take the derivative as if it was x to the 11th. Right, something to the 11th. What's the rule for something to the 11th power? What's the rule? The outside function goes first.
Turn that thing.
What?
11th.
So something to 11th. What happens with the 11th?
Comes down.
Comes down. That thing to the
10.
10th. Easy, right? We're not done. That's fundamentally something to the 11th. How do you always do anything like that? 11 comes down, and now whatever the shit it is, it's got 10 of them, right? Times, now the inside function gets its turn. Derivative of the outside function times derivative of the inside function. I love whenever I say derivative, it sounds a little drunk. It's in there. So what's the derivative of this?
4.
That was a lie.
4.
That was a lie.
4.
Cake is lying. 4. That sure as all hell beats writing this 11 times and multiplying that shit out, right? Oh, okay. No, yes, maybe, not really. Let's do a couple more, and then, of course, I've got a handout. All right, so what if I had, I like it. It's yummy. I do not think that word means what you think it means. So, what's the outside function? Cosine. Because you got shit inside of it, right? So you take the derivative of the outside thing first. You say to yourself, cosine of shit. What's the derivative of cosine of stuff?
Negative sign.
Good, negative sine of stuff. Then you multiply by the derivative of the inside. And again, I know some of you guys are like, I'm going to do that quicker. I'm going to do some of that stuff in my hand. You're going to make mistakes. You just are. Because I always have somebody come up to me. Maybe right now you don't see why this would be a question. But a question I always get is, how do you know when to stop with chain rule? Because then people just kind of, they do a derivative times another derivative. I'm like, what? There's no guessing. Is there any inside function in this thing? No. I really want you to realize that is its own little question. Don't say it's a chain rule problem, so there must be more chain rules. No. Is there something inside something else in you? No, it's not. It's polynomial, right? It's got a pi. Who gives a shit? It's a number. So that's polynomial. So what's that guy's derivative? What's the derivative?
2 pi x.
2 pi x
Minus 4.
minus 4. I love it. And really, the last step would be, this isn't that bad. You should bring that up front, just so it's a little coefficient. Doesn't really matter that much. Get out of there. So whenever the inside function is not just x. In fact, watch. I was about to say chain rule comes into play. Chain rule is always happening. So what do I mean by that? So if I have this, what's its derivative? Secant squared x. What's inside tangent? What's inside tangent? X. What's the derivative of x? What's the derivative of x?
1.
1. Okay. I really want you to see chain rule is always there. But when the inside is just x, its derivative is 1. Why write it? So I really want you to realize, we've been using chain rule this entire time. We just didn't actually need to realize we were, because the chain piece, the link, would just always be freaking 1. So who gives a shit? So it's always in play. It's just when the inside is more than the x, then it actually shows up. All right, so let me give you this here.
Professor,
Yes.
I didn't get one.
Oh, shit. Sorry, Shan.
Yes.
Connor, right? All right, now look. On the front of the page, let's do this together. I'll do these two at the bottom together real quick, and then I'm going to unleash you on the back. The back, you got all kinds of stuff. All right. Just do these two at the bottom. I've got ideas. I've got the formal way to write this shit. Here's that D by D stuff notation, right? In this case, it's a little confusing. It's a little better to look at it like this, but that's what it looks like in the D by dx Leibniz notation. So here's an example worked out. Here's an example worked out. So let's try this guy. What's the derivative of this guy going to be? Derivative of x is 1. Derivative of tangent is secant squared of stuff, and then the stuff gets a term. What's the derivative of 3x? 3. So then I can write this as 1 plus 3 secant squared 3x. Is that cool?
Wouldn't it be 3 plus 3 squared, secant squared?
Say again? Sorry?
3 plus 3 secant squared of 3x?
Why? What is this multiplied by? This.
Is it only that?
You tell me. If I wanted to multiply this thing by this also, what better be here?
Parentheses.
Yes. What does this get linked to? So this is going to be the part that has chain rule. So it's derivative times the inside derivative. This guy's got no chain rule going on.
Oh, yeah.
Separate term. No, it's a good question. Sorry, it may make it sound like with the shit. But I want you to realize that can only go so far. It can only go to its part that it's linked to. Oh, shit. Look at this guy. Ooh. This looks a little familiar, but now it's got a chain piece in it. What rule do I have to use primarily? Quotient rule. I love it. So you don't give a shit at first about chain. You don't care. It's primarily a quotient. So you start to attack it with quotient. So what would quotient rule say? Derivative of top times the bottom minus the top derivative of the bottom all over the bottom squared. So that's the quotient rule. It's supposed to be a little minus, but we'll do. So now when I do these derivatives, what's it going to involve, of course? Chain. So let's see, I get f prime of x equals. So what's the derivative of negative cosine?
Positive sign.
Positive sign, kick ass. 7x. And what's the derivative of the inside? Let's see if we can do this all at once. I know I said not to, but I'm running out of room. Times the derivative of the inside, which is, what's the derivative of the inside? 7, right? Derivative of 7x is 7. And that's times the 1 plus sine 7x. Minus 1 minus cosine 7x, and something very similar happens here. Derivative of sine is cosine 7x, and it's going to have another 7 because of chain rule. Is that cool? The chain rule says multiply by the derivative of the inside. I like it. All over this business here. And now it's just cleanup. Calculus is done. Now it's just algebra cleanup. So we get 7 sine 7x plus, I could have given myself more room, but I guess that was going to make it too easy. And then what's going to happen here is minus 7 cosine 7 plus 7 cosine squared. Put a square in there, Jeff. There you go, buddy. Right? Distribute this sucker. Bam. Bam. So what do we see that's already happened a few times today? Yeah, 7 sine squared plus 7 cosine squared is 7. The important thing, are you worried about the 7x inside at all? No, the important thing is they are the same angle. That's all that needs to be true for that identity to hold. So I get 7, that's here, this and this makes 7, plus 7 sine 7x minus 7 cosine 7x all over 1 plus sine 7x squared. Oh my God. Okay, so as soon as you're done writing that business down, turn that sucker over and start working on the problems in the back.